Dear students, welcome to Sia's digital classes. Today let us learn the concept of sample correlation coefficient. So let us check it out how it goes on. So sample correlation coefficient, let the observed correlation coefficient are a sample containing n pair of observations taken from a bivariate normal population. So we have learned in the last sim about correlation coefficient, right? The same correlation coefficient will utilize here to obtain our data. Whenever data will have small samples will have, to obtain that will utilize correlations here again. But here both will consider population correlation and sample correlation. So we need to know what is the population correlation and what is the sample correlation, like how we discussed with the mean, sample mean and population mean in this SEM. So like that we have correlation also, population correlation as well as sample correlation. So here we are considering observed correlation. Observed correlation is nothing but a sample correlation. The usual notation R will consider for observed correlation or the sample correlation. So n pair of observations we are considering. Yes, for correlation we need a pair of observations. We need to compare whenever we have comparisons. Whenever we want to drag the relationship, then we'll go for correlations. So we know that. So for that I am considering here n pair of observations and R is a observed correlation. So next, and again that all we are considering from the bivariate normal population, because it's a bivariate distribution. Whenever pair of observations we are considering, that comes out of bivariate population. So bivariate normal population, from normal population we are considering all this. So next, based on the null hypothesis H naught, rho is equal to 0 we are considering. Now rho becomes a population correlation coefficient. So rho is equal to 0 and considering under null hypothesis, which means population correlation coefficient is 0. So population correlation coefficient, just now I said population correlation will represent through rho. So that I am considering null hypothesis as 0. Okay, so that is the notation we have. H naught rho is equal to 0. So next, using this information, let us check it out what becomes our test statistics. So test statistics is given by small t is equal to, so the correlation coefficients we get through the t test. So in t test will represent through small t, notation is becomes t. So t is equal to r, our sample correlation coefficient, divided by root over 1 minus r square into root over n minus 2 becomes a formula to obtain our sample correlation coefficients. So this is your test statistics to obtain our correlation coefficient. Now let us check it out how the student t statistics goes on. So this statistic conforms to students t distribution with n minus 2 degrees of freedom. Yes, these are all small samples, so definitely we'll get degrees of freedoms also. So n minus 2 degrees of freedom we'll consider here. So student t distribution also will call t test. So under that n minus 2 degrees of freedom we have to consider for this correlation coefficient. Now how the conclusions will go on, or how the table values will go on, let us have a glance on that also. So t value, if it is significant or non-significant conditions, how null hypothesis is accepted or rejected, let us check it out. If it is significant, we'll reject the hypothesis, that is rho is not equal to 0 you will get, because rho is equal to 0 we considered under null hypothesis. So whenever we'll accept null hypothesis, there rho is equal to 0 we'll get. So here rejecting the hypothesis, we are saying it is significant, so we are rejecting the hypothesis, null hypothesis. So definitely rho should be not equal to 0, that we have already considered a null hypothesis. So through that, if it is significant, definitely will reject the hypothesis, it is rho not equal to 0 it will be. So R is significant of population correlations becomes our output or the outcome of the particular data. Next, non-significant, if it is non-significant t value, so what the hypothesis will be, which one will accept or reject, let us check it out. So here null hypothesis is accepted if it is non-significant. Obviously rho becomes equal to 0. That's what we consider under null hypothesis. So we are accepting null hypothesis, definitely rho will be 0. So rho is equal to 0. Variables are uncorrelated in the given population. So whenever it goes to rho is equal to 0, it goes, the variables will be uncorrelated. We have learned already, whenever correlation goes to 0, the variables will be uncorrelated. So that's what we specified here also. So that is your t values. Now let us check it out how paired sample t-test will go on. So paired t-test will call, so let us check it out that also here. So testing of two means can be accomplished when data are in the form of paired observations. So two means will consider whenever paired observations will have. So definitely two values will have in terms of paired observations, means paired paired data will be. So obviously we have to go for correlations, or a paired t-test will call, because in pairs we have the data. Pairs means like one data it is dependent on the other data. Like pair of shoes will call. What that means, if one shoe is spoiled or one shoe is unfit for you, definitely the other also will be unfit. That is in pair will be utilizing. One is dependent on the other. If one pair of shoes is spoiled, definitely they will throw, the other one also will shift for the new one. We can't utilize that. So dependent samples, whenever dependent samples we have, so one is dependent on the other. Without the first one, second one will not be, or without the second, the first one we can't handle. So in such situations, as a pair of observations will consider, and paired t-test will utilize for such type of data. So paired observations will consider here. In this pairing structure, the conditions of two populations are assigned randomly within homogeneous units. So we consider randomly here. That's what the point they are specifying here. Next, let x11, x21. So two samples we have to consider, two observations we have to use. So from the first set, first value. So x11 becomes the first value here from the first set. And next x21 from the second set, first value. So x21. So that becomes the first pair of observation. Next, the second pair of observation from the first set, second value. So x12, and from the second set, second value, x22. So like that, so on up to x1n, x2n. So up to n terms you are considering pair of observations. Then be a set of n paired of observations, where we assume that the mean and variance of the population represented by x1 are mu1. So mean and variances we are considering. Obviously again normal population will consider. So in normal population, mean and variances are mu1 and mu and sigma squares. So here also the same mean and variances I am considering here. But for two pair of observations, for x1 it will be mu1 sigma 1 square, for x2 mu2 sigma 2 square will be. That's what they have specified here. So mu1 sigma 1 square, and for the second set, that is for x2 set, mu2 and sigma 2 square, because they are dragged out of normal population. So these are the basic information we have. Let us utilize that one and let us check it out how the formula goes on. So defining difference between each pair of observation as di is equal to d becomes a difference between the observations. So di notation I am considering here. Di is nothing but the difference between the both the pair of observations. So simply x1i minus x2y becomes your di value. So I is equal to 1 to n, we know that. Next, di's are assumed to be normally distributed with the mean and variances. So again that also comes from the di values are also out of one normal population only will be derived. Yes, obviously, because x1, x2, whatever the x1 set, x2 set we are considering, that also we are dragging out of normal population. So di also comes out of normal population only. Next, what becomes the mu d then? That is mu d is mean for differences of the samples. So mu d becomes expectation of x1 minus x2. So obviously that two pair of observations you have to consider its expectation, that becomes a mean value. So expectation of x1 minus x2, take expectations inside, e of x1 minus e of x2 it will be, and it values we know already, we have considered x1 as mu1 and x2 as mu2. So simply I have substituted that values here, mu1 minus mu2 we got for mu d. So that is your mean for differences of samples. Next, let us check it out. The other things here, again we are considering the same samples. Then the same information we have here. Next, testing of hypothesis will be mu1 minus mu2 is equal to delta. Testing of hypothesis, mu1 minus mu2 goes to delta. I am considering some delta. Then can be accomplished by performing one sample t-test on mu d. Specifically, testing h0 mu1 minus mu2 is equal to delta against h1 mu1 minus mu2 not equal to delta is equivalent to testing h0 mu d is equal to delta against h1 not equal to delta. So I am considering one value here, and I am taking whenever the subtractions will go on the value, and whenever directly mu d we have how the testing of hypothesis will go on, that is h0 against h1, that values I am considering here. Now check it out, whenever like that h0 and h1 conditions we are considering, so what happens to the test statistics? Let us check it out here. So test statistics for testing mu d is equal to delta whenever we are considering. So formula will turn like this: t is equal to d bar minus mu1 minus mu2 by sd by root n. So d bar for differences of observations we are considering here. So this becomes a test statistics for paid t-test. So this is a formula, and again mu1 minus mu2 we considered as delta, right? So I have simply replaced that here. So d bar minus delta by sd by root n we got here. So next, so that becomes a t-test for us. Next, let us check it out how the d bar will goes on, and how its degrees of freedom will be for paid t-test. So which is a random variable with the distribution with n minus 1 degrees of freedom. So n minus 1 becomes the degrees of freedom for us. Next, where d is a sample mean and is given by d bar is equal to summation di by n. Yes, d bar is a mean, we know its formula, d bar is equal to summation di by n. If you do, you will get a d bar. And again sd square is a sample variance. The formula whatever just now we wrote, that whatever the values how we are getting, that we are specifying here. So d bar we have, right? So d bar is equal to summation di by n is a mean value we have. Next, sd square, to obtain sd square is nothing but sample variance we have. So we know the formula for variance, that is sd square is equal to summation di square minus summation di square by n minus 1. This is the same variance formula itself for sample variance we are considering. So the same variance formula in terms of x or xi we used to consider the same thing in terms of d we are considering here. So d bar value and sd square value will obtain in this way whenever we have a data, and finally we'll substitute that all in the formula of t, and we'll obtain the paid t-test answers. So this is your paid t-test values. Next, if at all we need confidence intervals also, how it goes on, let us check it out. So confidence interval for mu d, that is mu1 minus mu2 for paid observations we are considering now. So if d and sd are the mean and standard deviation of the normally distributed differences of n random pair of observations. So again n random observations we are considering normally distributed with d and sd values. So how the confidence intervals will go on, let us check it out. So a alpha minus 1 into 100% confidence interval for that will be mu d is equal to mu1 minus mu2 will be d bar minus t alpha by 2 sd by root n. So previously we discussed, and proportions and all the same formula according to the t-test it will be. So d bar is a mean for us we have. So d bar minus t alpha by 2, because it's a t-test, out of t-test we are considering. So we need critical values of t-test. So t alpha by 2 we are considering, and then into sd by root n, the formula we have here for standard error formula. So sd by root n less than mu d, the for mu d we are discussing this. So less than mu d less than d bar plus t alpha by 2 sd by root n becomes a confidence interval formula for paid t-test. So this is the formula to obtain our confidence intervals it will be. So next, where t alpha by 2 is the t value, we know that t alpha by 2 becomes the t value, that is our critical value, whatever based on the data we consider that. So t alpha by 2 is a table value we can call, with v is equal to n minus 1 degrees of freedom. Yes, we have degrees of freedoms also for small sample test. So t test is a small sample, so it has got here n minus 1 degrees of freedom. Area of alpha by 2 to the right side. So right side will get a, when you try to draw the graph to the right side, you will get this limits whenever you are trying to plot a curve. So this is your confidence interval formula here, d bar minus t alpha by 2 is d by root n, that both the limits will get. So we can plot into the graph also. So these are the confidence interval formulas, and so we discussed in this session about the sample correlation formula as well as paid t-test formulas. So these all comes under t-test. So t-test for correlation and t-test for paid observations. Whenever we have t-test for paid observations, that is paid t-test also we call. So this is the entire topic of correlation for t-test and paid t-test. So hope you have understood all the test statistics formulas as well as this confidence interval formulas. So see you all in the next session. Thank you.